Thank you to the organizers for inviting me. So I'll talk about laboratories, astrophysical laboratories for studying neutrino physics. Of course, a lot of people are familiar with this one, the early universe and weak decoupling and Big Bang nucleosynthesis. So the really interesting feature of this laboratory is that gravitation dictates the expansion rate. The gravitation is weak, so the expansion rate is generally very slow. And that allows really weakly interacting particles to actually come into equilibrium or otherwise affect the physics. So that's the allure of this. Also, the entropy per baryon is very large, at least on a nuclear physics scale. And that simplifies the nuclear physics of this epoch, which is nice, as you'll see. The other issue is that we know from the light element abundances from helium and deuterium that the lepton numbers are low, at least on a nucleosynthesis scale, they're low. The baryon number, of course, we measure in the CMB and from deuterium, and the baryon number is very low. This one is low on the standards of supernovae, but there's still a lot of room for mischief there. In any case, the low lepton number dictates that the neutrino-antineutrino asymmetry is small, and that's important. And the neutron to proton ratio, the deuterium production, the helium production, the relativistic degrees of freedom that freeze out, they're all sensitive to any BSM physics that alters the relationship between time, temperature, and scale factor. And moreover, this whole picture is very tightly constrained by the CMB observables and by other determinations of deuterium, for example, with 30-meter class telescopes. These will be determined by something like 1%. So anything that twitches here in the early universe is fair game, and we might see it because of this tight constraint. By contrast, stellar collapse and supernovae and by association, binary compact object mergers like binary neutron star mergers are a different situation. It's interesting, however, it's alluring that the weak interaction dictates all aspects of the evolution of these things. Very large electron lepton numbers, very much unlike the early universe. So the evolution is exquisitely sensitive to lepton number violation. So we're drawn like a moth to the flame here because this is alluring. Okay. And the entropy per baryon is quite different than in the Big Bang. It can be quite low, as we'll see, and it can be modestly high on a nuclear physics scale. And so it's the primary site for intermediate and heavy element nucleosynthesis. Many aspects are sensitive to neutrino flavor transformation, as I'll show you, and BSM physics. And it's important to realize that this collapse scenario is how we manufacture neutron stars and black holes. And bottom line, it's not well constrained. What did we learn from supernova 87A? We learned that the basic picture of collapse of a massive star to a neutron star is correct. That's the main takeaway from 87A. Okay, both of these environments are sensitive to flavor, mostly through these, I don't know what I did wrong here. Sorry. There we go. Through these charge current capture reactions. Note that these are flavor dependent. And at the energy scales we're interested in these two laboratories, only electron flavor neutrinos can change neutrons to protons and vice versa. Okay? So that's in large part what makes these environments sensitive to flavor. Okay, so gravitational collapse. So let's start with the standard model. I'll just set the neutrino mass standard model of stellar collapse, and I'll set the neutrino mass to 0 here. So we won't worry about any kind of BSM physics or neutrino flavor mixing. So the weak interaction dominates the evolution of these stars, and the progenitors of typical core collapse supernovae are kind of in this mass range. There's a succession of nuclear burning stages. And interestingly enough, the neutrino luminosity exceeds the photon luminosity from core carbon oxygen burning onward. So these stars are giant refrigerators. The neutrino emission from the cores of these stars lowers the entropy from roughly tens, sort of like the sun, to something more like 1 unit of Boltzmann's constant per baryon at the onset of collapse. The cumulative history of weak interactions, which are primarily positron decay of nuclei and electron capture on nuclei, lowers the electron fraction, that increases the neutron to proton ratio, and produces neutrinos which escape and lower this entropy. So the low entropy and the cold conditions, the pressure support is coming from highly degenerate relativistic electrons, and the core is, as my thesis advisor coined this phrase, trembling on the verge of instability. Wherever you have a self-gravitating configuration supported by particles moving near the speed of light, it's inherently unstable. So it's vulnerable to the GR instability, plus electron capture, because the electrons are supplying the support pressure, plus the whole situation is in nuclear statistical equilibrium, and as we change the entropy, you can shift NSE, and in any case, that lowers the adiabatic index and collapse is inevitable. Interestingly enough, the mass of this core that collapses is something like a Chandrasekhar mass, and that's proportional to the electron fraction squared, and that will figure in what we talk about in a minute. So it collapses from something like an Earth-sized white dwarf with a mass of the sun to a hot protoneutron star with a radius initially of something like 40 or 50 kilometers, and within a second or so, that's down to about 10 kilometers. So the collapse itself is characterized, as I just said, by really cold, thermodynamically cold conditions. The temperature can be 1,000,000 electron volts, but the entropy per baryon is of order 1. So that in some collapse equations of state, this collapsing core is a frozen crystalline solid. It's kind of Coulomb crystal solid. Interesting. High electron Fermi energy, as I said, much larger than the temperature, which is the order of few MeV. And we're in nuclear statistical equilibrium, so nuclear reaction rates don't really matter in this situation at all. The mean nuclear mass is quite large. These are not nuclei we can measure in a laboratory. And these large nuclei are in highly excited states. They may be sitting in excitation energies of 30 MeV or more above ground. So the nuclear physics is certainly exotic, and the weak interaction physics is likewise exotic. So there are two main channels of electron capture, so-called neutronization. Electron capture on these heavy nuclei, that heats the medium. It increases the entropy a little bit. I'll tell you why that's important in a second. Electron capture on protons, if the neutrinos escape, that actually cools the medium and decreases the entropy. So it's kind of a fight between these two processes. But notice that there are very few free protons around because the entropy is so low. So this process is really, it can be dominant just simply because the matrix elements for this capture are much larger in general than these. But the mass fraction of free protons is extremely sensitive to temperature. It's very low. So if you increase the entropy a little bit and increase the temperature, you can increase the proton fraction, and that in turn increases the neutronization rate. And you see where we're going with this. So eventually the neutrinos in this collapse are trapped by coherent scattering on the heavy nuclei. Remember, that's coherent scattering will go like the number of nucleons in that nucleus squared, and you can see that the number of nucleons is quite large. So that tends to be conservative scattering, and energy distribution among the neutrinos is mostly governed by neutrino electron scattering and some nuclear processes as well, like de-excitation of hot nuclei into neutrino pairs. So when these processes get going, we eventually come into chemical equilibrium, which we call beta equilibrium, and I put the protons and neutrons in quotes because they're generally in heavy nuclei, and there's some chemical equilibrium relationship between the chemical potentials. Now, I want you to look at this. If, for example, you were to turn on some kind of beyond standard model process that converted the electron neutrinos in equilibrium into some other species, then that would open a hole in this distribution of electron neutrinos, filled immediately by electron capture, likely going through heavy nuclei, which would increase the entropy. So you see that you're in a very unstable situation here. You see that it's quite sensitive to any lepton number violating process. Okay, neutrinos dominate the energetics of the collapse. The astronomers get excited about the explosion, which is only about 1% of the neutrino energy, which is really 99% of the gravitational binding energy drop when you go from this Earth-sized solar mass configuration down to something like like the Santa Barbara-sized neutron star. And that's 10% of the star's rest mass appearing as neutrinos. So you've got a lot of work to work with here in terms of neutrino energy. That's the gravitational binding energy. Once the neutrinos are trapped inside this core, they diffuse outwards, like a random walk process on timescales of something like seconds. And there's rough equipartition among all the different kinds of neutrinos. The other flavors are produced generally in pairs by thermal processes. So the shock in this infalling core forms at the edge of the so-called homologous or inner core. This is the part of the core that's falling subsonically. When it hits nuclear density, it hits a brick wall. The material in the outer core is falling in supersonically. So it hits this outer core, produces that red shock wave that then moves out. The initial shock energy is going like the 10/3 power of the electron fraction, which I told you is very sensitive to the integrated history of all the weak interaction processes, electron capture, positron decay, and any BSM physics that's operating. All those electron captures are determining this number. And you can see the shock energy is very sensitive to that. Now, the shock actually loses energy, as I'll show you in a second. When the shock comes through the edge of the neutron star, the neutrino sphere in a sense, you get the so-called neutronization burst. Okay, and so here's a picture from Tony Mesa Kappa, which is a very pretty picture. Here's that proto-neutron star I showed you. The shock moves out, but as the shock moves out, it shifts the nuclear statistical equilibrium towards alpha particles and free nucleons, and that costs energy, about 8 MeV per nucleon that's bound in a nucleus. You have to pull that energy out of the thermal energy in the shock. The shock loses energy and eventually stalls at a radius of order hundreds of kilometers. And then the idea is, from Beta and Wilson, I should have put that down here in 1985, is that the neutrinos radiating from this proto-neutron star eventually heat the material below the shock, delivering energy behind the shock, pushing on the shock, doing PDV work on the shock, and reviving the shock or re-energizing the shock. So that process depends on how quickly you can get energy out of the core. That depends on the equation of state. It depends on whether there might be convective motions in the core. It also depends sensitively, and the best models from these modelers, from the supernova modelers like Tony Mesa Kappa and Thomas Janka and Adam Burrows and Kai Kotaki, is that it's hydrodynamic motion that helps transport the energy deposited by those charge current neutrino interactions out to the base of the shock. So that's shown here. So that's the idea. The shock stalls at hundreds of kilometers. At roughly 100 milliseconds, it's re-energized by neutrinos on timescales of something like half a second, or it isn't. Don't really know. Some of these models don't explode. So nucleosynthesis, Gail McLaughlin and Amol will talk about that a little bit later this morning, and I direct you to Rebecca Sermon's talk from last week. So both the light elements in BBN and the heavier mass nuclei, like R process or P process nuclei, I contend to represent a fossil record of neutrino physics that was operating in the Big Bang or in these stellar collapse environments. So in the stellar collapse environment, well, you can ask then, does that fossil record of light elements and heavy elements, does that conform with, is it consistent with what we know from light element abundant systematics and effective and et cetera from the CMB? Is it consistent with hopefully a measured diffuse supernova neutrino background? Is it consistent with what we're learning from LIGO and Virgo and soon CAGRA on compact object systematics? Is it consistent with what the astronomers and astrophysicists calculate or estimate or measure for the mass assembly history of galaxies and structure? And finally, is it consistent with what the astronomers' constraints are on chemical evolution? So those are the big questions. Let me just say there's more than a passing resemblance in the physics of Big Bang nucleosynthesis, the nuclear physics of nucleosynthesis in BBN and in a an outflow from a supernova. And I apologize to everyone here who's seen my slide 100 million times, but it's important. So if I look here at the early universe, this is expanding this way, time's going this way, temperature's going the other way. The neutron to proton ratios are always set by these reactions, which are flavor dependent. And so in the Big Bang, where there are sort of comparable numbers of nu E's and nu E bars, the ratio of neutrons to protons is less than 1. And so the nuclear physics here is extremely simple because the assembly of nuclei is really just a fight between entropy, between disorder and binding energy. So it costs a lot of entropy. It costs a lot in terms of disorder to put nucleons inside heavier nuclei. They don't make any because the entropy is quite high. So what happens is that every nucleon that can be stuck into an alpha particle is so stuck into an alpha particle. And so in Big Bang nucleosynthesis, you make alpha particles and you're at low temperature a sea of protons, free protons, and that's it, you're done. Because the Coulomb barriers will prevent any assembly of anything else. Oh, sure. You know, 1 neutron in 10 to the 5 winds up in a deuteron. That's very interesting, but it's a trace amount. 1 in a billion or 10 billion winds up in a beryllium-7 or lithium-7 nucleus. By contrast, the outflows that Gail and Amol will talk about are kind of the isospin mirror of what happens in Big Bang nucleosynthesis. That's because the nu E bars can be more energetic than the nu E's. And so you can drive the material neutron rich. Now the entropy is lower than the Big Bang, but on a nuclear physics scale, it's still large. So that the basic nuclear physics of alpha formation is the same. You scour out all the protons in this case, and you're left with a sea of free neutrons. Neutrons have no Coulomb barriers. You could wind up with uranium over here. Okay. So here's a post-explosion. Here's a somewhat more detailed version of what might happen in an outflow from the material moving out from a neutron star. This is alpha-rich freeze-out, and Amol will talk about this, I think, some more. There are kind of 3 knobs that the models can turn. And ideally, if you want to make something like the R process, like uranium, you want a very high neutron number per every seed nucleus that you're going to capture neutrons on. And you can kind of turn the knobs this way to optimize that neutron to seed ratio. You could turn up the entropy. That will reduce the number of seed nuclei, which ironically is absolutely helpful. You could just brute force increase the neutron to proton ratio, that is reduce YE. Or you could have the expansion timescale really short. And that helps because you get seed nuclei, you have to go through these 3-body reactions like alpha, alpha, N to beryllium-9. So if there's less time in the expansion to do that, there'll be fewer seed nuclei. So that's good. And of course, there's the neutrino signal. I've taken this from the Maritzi paper, and we'll talk about that later. One thing I'll bring to your attention, of course, is that just an interesting fact about gravitation. Of course, when stars cool off, they heat up. So you'll notice that that the average energies of neutrinos here increase for a while, right? As the star contracts, gravitationally contracts. So now let's look at the case where I turn on neutrino physics, neutrino flavor mixing in particular. Okay, so first we'll consider a mean field treatment of this, where neutrino and antineutrino evolution in time, momentum, flavor, and spin space is the objective. So there are the so-called quantum kinetic equations, and I refer you to Lucas John's talk last week, which was really very good. So here's what an equation looks like. Here's what the quantum kinetic equation looks like in this case. The left-hand side is some kind of advection term operator on a density matrix. There's a coherent evolution piece, and then there's a collision piece. Collisions, of course, this is a quantum mechanical operator, so it can mediate transformation of flavors because essentially collisions are something like measurements. So these density matrices are like 3 by 3 like this, and the diagonal entries of the density matrices essentially are equivalent to sort of number densities or occupation probabilities. The off-diagonal entries encode quantum coherence. And likewise for these collision terms, which are quite complicated, actually. I should have put a reference to Blaschke and Triliano, 2016, that calculated these for the first time. And I'm ignoring spin degrees of freedom. Actually, if you really write down the full quantum kinetic equations, they're really 6 by 6. So these density operators would include antineutrinos as well, and there are off-diagonal terms there that are related to spin and related to spin flip that couple neutrinos and antineutrinos in the case of Majorana's case. I won't talk about that, but it's still nevertheless very interesting, and we'll come back to that if there's time. So the first thing you can imagine is a classical calculation where you ignore quantum coherence entirely. Okay, so this is Boltzmann neutrino transport, and it would look something like this. Historically, what we did first is consider a purely coherent case where we turned off all collisions and just kept that one term, a Hamiltonian in the coherent case that has vacuum oscillations, neutrino electron, forward scattering contributions, and then this one, neutrino forward scattering. That's what causes the nonlinearity in this problem. So the point is that the potentials in the medium that govern flavor transformation of neutrinos now depend on the flavor states of the neutrinos. So it's fiercely nonlinear. Here's what that Hamiltonian can look like in a bulb model. And there are two takeaways from this. One is that this is the Hamiltonian for a neutrino of momentum p. You can see that the Hamiltonian depends on the intersection angle of the neutrinos in forward scattering, which makes sense, right? So two neutrinos that are collinear and on null trajectories moving at the speed of light are never going to forward scatter on each other. So the potential that brings in is zero. And so it depends on the directions. It also depends sensitively on the difference between neutrinos and antineutrinos. And so when we were able to do these calculations, we immediately saw this rich phenomenology of spectral swaps and collective oscillations. And so a kind of a classic thing here is to, in this coherent case, is to look for instabilities in the flavor field, and there are many instabilities. And I refer you back to Luke's talk last week. There are slow types that were known for a long time. There's fast instability. There's collisional instability, including this paper recently by Luke Johns that leverages the difference in the scattering rates between neutrinos and antineutrinos. Very interesting. So typically what we have done is to combine a classical calculation, like from the simulators, with a coherent calculation. So we'll use the classical Boltzmann calculation to get the lay of the land, the distribution of neutrino energies and directions in the neutrino flavor field above the neutron star, for example, and then go from there. So one interesting idea we realized early on, this is a paper by J.J. Cherry and Alex Friedland and company, and so is that in these bulb models, the neutrinos are far away. They're coming from a narrow cone of angles. And I just told you that the neutrino-neutrino coupling is low in that case. So the odd neutrino, maybe 1 in 1,000, goes out here somewhere, scatters on a nucleus, and comes back in at some odd angle. So that will make an outsized contribution to the potential. That we call the halo. And we can kind of also leverage these classical Boltzmann calculations to look at electron-lepton number crossings where you're likely to get fast flavor conversions, for example. So here's a paper by Hiroki Nagakura and Luke Johns and Burrows looking at that. And there are several different kinds of electron-lepton number crossings. And here's radius for the shock wave in red here for an exploding model, red dash for a non-exploding model versus time, the scale of about 1 second. And you see that there are various kinds of types of these electron-lepton number crossings that depend on whether the electron-lepton number, there's a dominance of nu e going outward and nu e bar going downward, or vice versa. Okay, and we can also We tried this, Luke Johns and Hiroki Nagakura and Burroughs and I, looking at trying to figure out some way we could put a package into these big supernova simulations codes that would actually kind of mock up the main features of neutrino flavor transformation. We failed. And instead, what we did is we learned something about flavor transformation. So the point is that the Boltzmann classical calculations use a moment method to solve the Boltzmann equation. So we said, we're just going to try to piggyback on that, and we'll have a quantum moment method to do this, which was kind of stupid, really, if you look back on it, because we needed something like 1,000 angle bins to get convergence. Alex is nodding to me. Yeah. So this was crazy. But we learned something very interesting, which is that the transformation power seems to cascade with time from larger scales down to smaller scales in something like a turbulent cascade. Finally, we can do we can really do full quantum transport, the full solutions of the QKEs. We can do it for the early universe. Julian Fruzzi and Cyril Pitrot have done this recently with a small change in the effective number of degrees of freedom that results from a quantum versus a Boltzmann transport calculation. Evan Groves has been working on this and can actually do this better. And he's still working on this, but here's the difference between Boltzmann in B and quantum transport. The point is that a neutrino, if I put in oscillations now in the early universe, an electron neutrino is spending part of its time as a mu or tau neutrino. But the electron neutrinos have a charge current scattering channel that the mu and tau neutrinos don't have. So interestingly enough, when we put in the quantum effects in the QKEs, the results, the spectral distortions are somewhere between what we get for Boltzmann and in the two different cases for the flavors. We can try this for core collapse supernovae. An isotropic case has been solved by Sherwood-Rickers and Gale and Jim Neller and Alexei Vlasenko in this paper. There are also promising particle and cell techniques which are ongoing right now. Here's a nice paper on how to do that, and also Monte Carlo techniques for solving QKEs. So that's coming. So here's a takeaway. Neutrino flavor transformation feeds back on the hydrodynamics and transport, temperature, entropy, nuclear composition, equation of state, and vice versa. So you can't ignore feedback on flavor conversion in the medium, and you can't ignore the medium's feedback on flavor conversion. Here's an example, a kind of in-your-face example from work by Payel and Friedland. Shock adiabaticity modulation of supernova neutrino flavor signal. Here's the shock. Alex talked about this last week a little bit. And there's a difference in the neutrino signal you get from that effect. Finally, you could question now the efficacy of this mean field of treatment. So I direct you to this paper by Michael Servia, Amol Patwardhan, and Baha, and Calvin Johnson, and Coppersmith on entanglement and collective flavor contributions in a dense neutrino gas. I find this paper to be terrifying. So they can't treat many neutrinos. Keep in mind, there are roughly 10 to the 58 neutrinos that are in the supernova environment. Okay, in this calculation, they go up to 10. But you can see something very disturbing here, which is that the entanglement entropy increases as the number of neutrinos increases. Remember, entanglement entropy is a measure of the inability to treat this neutrino gas as simply a product state of different individual neutrinos. Luckily, here's more recent work in a more sophisticated treatment by Patwardhan et al. Maybe they can talk about it later, but now I see that the entanglement entropy is large at, I said resonance, but I really meant the spectral swap at the swap energy. So maybe that makes sense to me. but it's still worrisome. And so this is still kind of early days with this. Finally, let me finish by talking about beyond standard model physics. So beyond standard model, I just told you how, the whole supernova story is sensitive, very sensitive to lepton number violation. That's interesting. So much of the standard picture of supernova core collapse could be sensitive to that. And also maybe core physics and the R process. And so I think Anna Saligo will talk about that next. So there are all kinds of ideas for non-standard interactions. We've heard about some of them as explanations for the anomalies. For example, there's this great paper, there's this white paper actually on a summary of potential issues. This Bertuzzo et al. Physical review letter is quite revealing. There are lots of ideas. Some of them look like this. And I'll just draw your attention to this. They involve sterile neutrinos, maybe dark Z's, a dark sector. They also involve coupling of quark currents, standard model quark currents, and neutrino currents, either dark sector neutrinos or standard neutrinos. That could be very important in this whole collapse picture. Lots of intriguing possibilities in the dark sector, and I can remind you of some of these. Low reheat inflation, which we heard about from Graciela yesterday. Non-standard secret interactions among the sterile neutrinos themselves. So here's some papers on that. Here's one by Joachim and Basabu. And kind of my favorite in these is this one by Cherry, Friedland, and Shoemaker, which is very interesting. If you have neutrinos, sterile neutrinos that have their own rich self-interacting sector, then you can do interesting things in producing sterile neutrino dark matter, for example, that will evade your bounds, Kev. For example, this paper by Mani Brodesen and Andre, for example. And this one by Luke Johns and myself. Okay, so summary. For compact objects, neutrinos transport and carry much of the energy in core collapse supernovae and, by extension, other compact object environments like binary neutron star mergers. This physics is flavor dependent. These environments are sensitive to lepton number violating physics, neutrino non-standard interactions, sometimes in unique ways. So that's the allure here. Unfortunately, these are not well constrained by observation, but there are some handles we have that are promising. Nucleosynthesis, the diffuse supernova neutrino background, the growing body of insight and evidence on gravitational waves and compact object systematics, maybe someday a signal. And a kind of overarching feeling that I have is that toy problems, which are things that we do in this field a lot, because that's all we can calculate, that do not include all the relevant physics and or build-in symmetries in the medium may be revealing of interesting phenomenon, but misleading in what happens in nature. And on the early universe side, any physics that alters the time, temperature, scale factor relationship could show up in measured values of deuterium, helium, and ineffective. Those three things will be measured with 30-meter class telescopes, deuterium to about 1%. Better than that, the helium and ineffective from stage 4 CMB. And different BSM scenarios can move these three quantities in different ways that might be unique fingerprints for specific BSM scenarios. And this is very well constrained by observation and promises to get even better. So you can look in the CMB S4 science book, for example, and see that. Thank you.
Thank you so much. Thank you for leaving ample time for questions. Are there any questions or comments?
Since the scope is huge, there are so many things one could ask. There was this great thing that you did a while ago with Phil Lamanick, right, on these non-conservation, flavor non-conservation effects on the core. Has that been followed up?
No.
No, that's shocking, no?
Yeah.
Is that
no pun intended?
No, but
yeah.
That's like a first order effect.
There's so many things. This is such a target-rich environment for physics, and there's so many things that can affect that core physics, and that's certainly worth following up on.
Other questions?
I wanted to ask about, you mentioned that the shock energy has a lot of information that can tell us about the inner workings of the collapse. So what would be an observable for the shock energy that we can detect in the next supernova?
Okay, it's an excellent question, but it's sort of above my pay grade. You have to trust these large simulations to connect shock energy and re-energizing the shock with fundamental neutrino physics. So I can't tell you whether the failure of the shock to be re-energized is coming from fundamental neutrino physics, like we don't know something about the way neutrinos interact, or whether it's coming from some approximations made in those simulations. I know that's an unsatisfying answer, but I think it's true. Maybe Tony Meza-Kappa and Thomas Janka and Kai Kotaki and Adam Burrows would disagree with me, but that's just my opinion, okay? Mm-hmm.
When you referred to the impact of gravitational wave observations, you were mostly referring to the compact object statistics that we'll get as we collect data. What about the gravitational waves from an individual supernova?
Oh, that's a really good question. I had a slide, but decided I didn't have time to show it. We don't know what this, unlike compact binary in spiral mergers, this is for the other meeting, right? With in spiral mergers, we know exactly what the signal will look like. Right? And they have a template of different signatures that they can search for. Unlike that situation, for core collapse supernova, we really don't know what we're looking for. So most of the gravitational wave signature will come from moving nuclear matter in some non-spherically symmetric way in the neutron star. But some will come from an asymmetric neutrino burst itself, and that's intriguing. So there's some papers that a student and I wrote on this, and also one by Cecilia Lunardini and her student, which I find very interesting, where we can actually look at the memory signature, the memory signal from the gravitational wave pulse from the neutrinos or other particles coming out of the core, and learn something about that. So if I had dark photons coming out or axions coming out, for example, or I did something weird to the neutrinos, enhanced cooling in some way, would that alter that signature? We're not there yet. We would need another generation. It's LIGO and Virgo and Cagra are not really sensitive in the frequency band we would need to do this. Something like Desigo that's sensitive in the eponymously named decihertz range is almost ideal for this, and the sensitivities they can get are great. And so we could look at the actual memory signatures, memory signals.
So I have a question. Could you say a few more words about the neutrino halo? And the reason why I'm asking is because self-interactions amongst the neutrinos can also probably change that picture a lot. No?
Oh, that's a great point. And yeah, I can find the neutrino halo. So we don't really know what this halo does. So, Alex and I and a few others pointed this out, and not much has been done with it since. There's a calculation by Shashank Shalgar and Vincenzo Trigliano and Mark Paris that looks at the effect on is essentially the outflow physics and flavor transformation, and they find a relatively small effect. They say it's a small effect. They actually kind of change the electron fraction by about 10%, but in location of where the neutrinos decouple and where the flavor transformation sets in. And that sounds like a relatively small effect, but it could actually be important in some of these nucleosynthesis models that I think Gail will talk about, for example. So that's just to answer part of your question. The other part is that, of course, if you add non-standard interactions out here and enhance the scattering, then you'll increase this halo effect. And I can imagine that that shows up. You can look at these papers, and we calculate the alteration in the collective modes, and it's significant. There's another aspect to this, which was pointed out by John Cherry recently, which is that there's a time delay, a time of flight halo effect also. So that, early on, the neutrino luminosity might be quite large, and later it falls off. But some of those more energetic neutrinos might actually be scattered downward from some location far out in the envelope and contribute to this. And of course, some of these effects in flavor transformation are energy dependent.
Thank you.
Other questions or comments? If not, let's thank George again.